we'll talk about ICMP. This is where ICMP lives, if you will. I made air quotes because it's a helper protocol that rides on top of the network layer. So it rides on an IP datagram. So from the diagram you can see there's a IP ICMP data with an ICMP header, and that gets put into a network layer packet with a network layer header. So that'd be IP. Normally, people talk about ICMP, they refer to it as like a layer 3 protocol, although it's really a helper protocol that goes along with layer 3. So that's how you should probably refer to it. Just to review some things we've talked about so far, in particular with regard to the IP protocol. IP is connectionless and unreliable. It makes little effort to detect and correct errors. There's a checksum in the header that it uses to try to detect some types of errors, but in general it doesn't really concern itself with errors. So let's talk a little bit about what that means. The stack will detect and report errors using the ICMP protocol, but when we say IP itself doesn't, that means there's no mechanism built into the protocol. Like with TCP, we do sequence numbers and sends and ACKs and all that kind of stuff so we can make sure the data gets sent. Well, IP does not have anything like that built into the protocol. If for some reason the packets can't be delivered, then it will use ICMP to report, the host or gateway will use ICMP to report that information. And why is that? Because errors are important. We may not be concerned with error checking at the network layer on every single packet because most of the time we assume it's going to work. But if there is an error, we want to be able to report it. So ICMP is the Internet Controlled Message Protocol. It was originally defined in RFC 792. It's been extended by some other RFCs that have come along, but that's where it started. Here's the next line is straight from the RFC, which I didn't need to do any massaging on because it actually pretty concisely states why we need ICMP and what it's used for. So the Internet Protocol is not designed to be absolutely reliable. The purpose of these control messages is to provide feedback about problems in the communication environment, not to make IP reliable. There are still no guarantees that a datagram will be delivered or a control message will be returned. Some datagrams may still be undeliverable or undelivered without any report of their loss. The higher level protocols that use IP must implement their own reliability procedures if reliable communication is required. So what that basically says is, hey, we'll try really, really, really hard, but we're not going to guarantee it's going to get there, and we're also not going to guarantee you're going to get an error message. If you want to guarantee it's going to get there, you need to use a reliable higher level protocol, and the reliable higher level protocol that we use is TCP. So if you need reliability, TCP. So there are a couple of rules about ICMP. One is that no ICMP messages are sent about ICMP messages. So if you send an ICMP error message that can't be delivered, then that's not going to generate an ICMP message back to the router that sent it. First off, it just creates extra traffic unnecessarily. And second off, the router that sent the ICMP error message doesn't really care if you got it. It was trying to do you a favor. It was trying to let you know that it could not deliver your datagram. So to send it an error message telling it that you couldn't deliver the message that it was trying to be friendly and deliver is kind of a waste of resources and not really necessary. The second rule defined in the RFC about when to or when to not send ICMP error messages is that ICMP messages are only sent about errors in handling fragment 0 of fragmented datagrams. So if there's 4 fragments, then it's only going to send one error message, and it will send that when it receives the first fragment. So there are two types of ICMP error messages: query messages and error reporting messages. Query messages normally come in pairs. You will send a request to the server or to the other host, and you will expect a response from that other host. Error reporting messages are used to report communications issues, and we'll go through the main types of messages we can look at. So ping, we are all familiar with ping at this point. Under the covers, ping uses the ICMP protocol. It sends an echo request, and the other side will reply with an echo reply. So here's what the ICMP header and data portion looks like in this case. all ICMP error messages share the same first 4 bytes. That'd be the type, the code, and the checksum. The type and code are used to determine what type of error message it is, and that's important because they have different layouts that need to be interpreted differently depending on the type. The checksum, rudimentary error checking. For ping packets, we also have an identifier and a sequence number, which if you read the RFC, it says that the identifier and the sequence number may be used in order to try to determine which pings go with which streams. So, in theory, if you start 5 different pings on your machine, the identifier on the first one will be 0, the identifier on the second one will be 1, the identifier on the third one will be 2, and so forth. And the sequence numbers, every time it sends a ping, in theory, the sequence number will increment by 1. So the first ping would be 0, the second ping would be 1, the third ping would be 2, and that way the receiving host could detect if it got the pings and which ping it needed to go to if you had several pings running when you got the replies back. The data is just random data that's built in to fill the packet. You can specify the packet size when you do a ping with a ping-L, I believe, on Windows. You can specify the packet size, so that data will be how much data. The data will be random data that consists of the amount of data you said to send. I call it random data, but it's really not random. If you look in the data portion of an ICMP ping, you'll see that it's mainly ascending characters. So take a look at that if you get a chance. So that would be a ping, echo request, and an echo reply. There's some other query messages that we're not going to talk about because they're really not all that helpful or useful anymore. They still exist, and we'll actually try to send some in the lab just to see what happens. That'd be a timestamp request and reply, information request and reply, and an address mask request and reply. Those messages aren't really used very much, so we're not really going to talk about them. We get to error messages. Error messages, like we said, will be sent when a host or a router detects a problem that will prevent a datagram from being delivered. The first type of error message we're going to talk about is destination unreachable. It has the same first 4 bytes we looked at with ping, the type, the code, and the checksum. The second 4 bytes for this particular type of message is unused, and then the last portion we show in our header is the data. Interesting thing, to me anyway, interesting thing about ICMP error messages is the data portion of that error message is the datagram that caused the error condition that generated the message. So for example, if you recall from our discussions of UDP, I said if you send a UDP datagram to a port that is not listening, you will get a destination port unreachable message. Well, now we can say, hey, that's type 3, code 3. Destination port unreachable. Well, when this error message goes back, this data will be the first part of the UDP datagram that caused the problem. So this will be the original IP header and the first 64 bits of IP data, which is the first 8 bytes of the upper layer protocol data. So that gets you that will get you all the UDP header because it's only 8 bytes in length. So this is how you can determine where the error came from. You can look at that upper layer protocol header and say, oh, this was from this was to port 53, so this is a DNS request that couldn't be delivered. So that's what the data is. The data is the datagram that caused the problem. Type 3 is destination unreachable. Some of the codes we have on here, code 0, net unreachable, code 1, host unreachable. Those will come from a router saying I don't know how to get there. Mainly the routing table doesn't have anything in there. Protocol unreachable, that would indicate that say you're trying to go to a machine. Let me think about an example for this. I want to make an actual useful example. Say you send a UDP packet to a host that for some reason does not have a UDP protocol. That's not a realistic example because UDP is always going to be running. But say you send a UDP datagram to a host that's not running UDP, then you would get a protocol unreachable. We already talked about type 3, code 3, port unreachable for UDP traffic. UDP traffic to a port that's not listening will get a destination port unreachable. Just for purpose of review, a TCP packet to a port that's not listening will send a TCP reset. Right, remember that? For fragmentation needed and DF set, we're going to do that in the lab for fun to generate some error traffic. Basically, we need to send a packet that is larger than the MTU with the DF bit set, and that will cause us to get that error message back. And source route failed. If you recall, I believe we briefly mentioned the IP options. One of those options is strict source route and loose source routing. And if you specify a source route that cannot be completed, you will get this error message: type 3, code 5, source route failed. A time exceeded message, similar header to the destination unreachable message. Type 11, code 0, time to live exceeded in transit. Remember, the routers decrement the time to live every time it passes through a router. Once it gets to 0, it gets discarded, and this error message type 11, code 0 gets replied. And then fragment reassembly time exceeded. With fragmentation, we're going to break large packets up into smaller packets, and we may need to wait some length of time before to reassemble those packets, right? We're expecting more fragments to be coming, so we will wait some length of time, but we're not going to wait forever. So eventually we will give up and discard the fragments we did receive and send back a type 11 code 1 time exceeded error message. Parameter problem, that's if something gets corrupted in the IP header. You'll send back the parameter problem message. It includes a pointer that points to the byte in the header that is screwed up, and that'll be type 12 code 0. Source quench, if we have to drop packets, the router's dropping packets because the buffers are full, it may elect to send a source quench message to machines asking them to stop sending traffic so quickly. Type 4 code 0. Redirect message, this happens if there is more than one router on the same LAN and you send the traffic to a particular router and it is going to route that traffic to another router on the same LAN. So for example, say you have a default gateway on your LAN, but then you have another router somewhere else that's used for special traffic. It is possible that if you send traffic to your default gateway, it may send you a redirect message telling you to send the traffic to that other router. And the header for that, same first line, and then the second line we have the IP address of the other gateway, and then the data is the original datagram that caused the problem. So to summarize, IP is not reliable, has very limited error checking. IP does not include any mechanism to report or correct errors. We use ICMP to report errors, and if you need to have reliable communication using the IP protocol, you need to use an upper layer protocol that will guarantee reliability. And that upper layer protocol, as we should all know at this point, is TCP. Questions? Put them on the discussion board, bring them to class.